Okay, the recording has started, so we will dive right in. My name is Tosh Cornwell. I am a second year grad student, and I will be going over differential expression analysis over the next 2 days. The material for this week will be pretty R heavy, as a lot of the analysis done for differential expression is done in R. And both of the lectures will be broken up into just kind of a section where we will talk about the basics behind what we're doing and behind differential expression analysis. And then we will do a live demo using R. So I'm going to start right from the beginning, and I'm going to share my screen. So on the Bio20 website, the slides have been posted. They're right here. And I am going to present these, and then we'll do the demo afterwards. So, on the slides, for those who want to follow along, there's this link. This link will be to the Google Drive folder where I have put some other things that we'll need later. For now, though, you can just follow along. We're going to talk a little bit about what differential expression analysis is, and then what the inputs are for it. We're going to talk about handling of the data, preprocessing and normalization. We're going to talk about some differential expression tools, and specifically what it is we will use to perform the analysis. And then we're going to talk about the interpretation of the result and the visualization of the results. I'm not sure how much we're going to get into the visualization today. I don't think we're actually going to do it at all. We'll save that for next time, but we'll see how far we get. So differential expression analysis is essentially the process of just analyzing differences in RNA expression between multiple samples and groups. So in the end, this boils down to you have some type of cohort, and most oftentimes this will be done as a pairwise analysis, A versus B. To perform this analysis, there are two necessary inputs that you need. One, you need your count data. This is the metrics by which you measured your RNA expression. Now, this can take a few different forms depending on whatever medium you're using, specifically microarray versus sequencing data. For most of this, I'm going to focus on actual RNA sequencing data, so count information as opposed to microarray data. Although the tools are similar and the concepts are the same, I find that most analysis done nowadays is in using sequencing counts. And so I feel like it'd be most helpful when we go over those things. The second input to the data is the metadata. So metadata is literally the data about the data. And this is the input that will inform the information about your samples. So this includes, most importantly, what groups they belong to. So when we do our A versus B analysis, we need to know what samples fall into A and what samples fall into B. But your metadata will also be comprised of the information that can be used to, one, either further inform the comparison you're making, if there's some kind of either paired analysis, batch effect, or any other kind of variables that you want to control for, or at least include in your model. Or two, if there's any information you want to use in later visualizations, you can leave in the metadata and then just not include in the model. So count data, as I mentioned, will most likely nowadays be in the form of RNA expression data in physical counts, which is literally the product of counting reads as they're aligned to specific areas of the genome. So this means that the count data that you should be starting with is going to be raw whole numbers. So raw meaning it has not been already normalized or processed. It is literally the output of feature counts or HT-seq or whatever that gives you just an integer measure of how many reads align to that area of the genome. And two, because of this, they will be whole numbers. Now, sometimes you'll be given count data and you'll see that it's not whole numbers or anything like that. If it's not whole numbers, if it doesn't look like this, then that means your data has been somehow processed already. This means it may have already been normalized, it may have already been filtered, it may have been transformed with some kind of log or other type of mathematical transformation, or again, it could be kind of a relative abundancy measure, so such as a lot of microarray data. But for our purposes, we're going to focus on RNA sequencing data, so raw counts. As I mentioned, your metadata is your data about your data. And the most important aspect of this is your groups. You want to know which one of your samples fall into which category. And so along this line, you will have your samples listed as so, and then your columns will contain whatever metadata you need for your analysis. As I mentioned, you need to have a grouping column, but you can also have any additional information here to either one, include in your model, or two, just leave attached for further analysis later when you're trying to visualize your results. Lastly, I should mention that sometimes you can actually have metadata on your features as well, so for on your genes. Although we won't be covering any of this today, sometimes it's important to have information about your features to further inform your analysis. So for example, when you have alternative splicing analyses where you have multiple isoforms for the single gene, you will have your features be the individual isoforms, but you may want to include what gene each of these isoforms which family they're part of. So along those lines, you can include that information in an additional metadata table about your features. Again, not something today, but something to be aware of. So once you have your inputs set ready and you have your metadata and your count data, the first step before you do any type of analysis is some basic pre-processing steps. Now, a number of tools will actually say that you don't need to do any kind of filtering, but in general, it's still a good idea, and many workflows still start with this step. So first, you're going to want to filter out low expressing reads. Now, this can be done in a number of ways, and there's not really a right way to do it. You'll see here I mentioned that in two of the tools we'll be mentioning, the DESeq2 and Lemma, in their vignettes, they both have this kind of arbitrary count of 10, as in if there's at least 10 counts of that gene across all your samples, it's okay. My favorite filter is this concept here, where you have the N number of reads and S number of samples. So for example, at least 2 reads in half of your samples. By doing this, this will allow you to filter out genes that not only are either just low expressing, but may also be a complete outlier in 1 or 2 of your samples in a large experiment. And by doing this, you can filter those out that seem to be aberrations. Now, again, sometimes you might want to do this if you have only a couple of samples and you want to make sure that you keep in these things that might be extraneous or outliers. Then you want to include this. But in general, I think this is a pretty good way to go. N number of reads and S number of samples, and then I like to do either 2 or 4 in about half of your samples. The other pre-processing step is normalization. Igor touched on this previously, but I'm going to go over it again, but mostly in a broad strokes manner. I'm not going to get into any of the math of it because a lot of that is not actually necessarily pertinent. So a lot of these tools have normalization already built in, so this will not be a separate step you will do yourself, but it's still an important concept to understand. Normalization is a crucial step to your analysis because, as many of you may know, when you do a sequencing experiment, the library depth, or the number of reads you get per sample, can be very, very different. And what we really care about are the differences in the abundances of the different features across your samples, as opposed to the raw numbers. So normalization is the method by which we go through each of our samples and essentially get them on the same playing field. Now, there's many ways to do this, and the preferred method has evolved over time. RPKM, or FPKM, stands for reads or features per kilobase per million reads. This method was in favor for a long time and was the standard by which many workflows followed. Basically, this method normalized by not only the number of reads, but also the length of gene. And people suspected that this was the best way to really account for any kind of variation between your samples that isn't biological. In reality, this has actually fallen out of favor and has proven to not be an effective means. And in fact, it can skew your data in certain ways that make the results unreliable. Nowadays, people favor some of the methods actually built into the functions like lemma and deseek. Specifically, deseek uses a method called the median of ratios, and lemma uses trimmed mean of m values. Again, I'm not going to get into the math of any of this, but just know that the normalization methods used by these tools are the preferred means. Now, if you are not using a package and you want to normalize your counts for another reason, for example, just for visualization, and you're not using any of these preset methods, I would recommend upper quartile normalization. Upper quartile normalization is basically where you take the upper quartile, so the 25th percentile of value for each sample and divide all of the counts by that value. By doing that, it tends to normalize your data pretty well, but also tends to deal with skew better than other normalization methods do. So there are a number of differential gene expression tools out there. And frankly, if you pick one of the good ones that people tend to use, there really isn't a right answer. I will say though that because there are so many, there are some that are kind of defunct and out of play anymore that are kind of frankly the wrong answer. But if you stick with one of these, one of the big three of DE-seq2, lemma, or edgeR, you'll probably be fine. All of these packages are R packages, supported by the channel bioconductor, which it may have been touched on before. Bioconductor is a specific repository of R packages that's highly curated and well maintained. The vignettes for these are quite good. I included these as clickable links within this PowerPoint so you can see for yourself. They really go into a lot of detail and they provide a lot of information. In some ways, they're overly informative because they will actually go into the very specific modeling of what it is they do. And I suspect that many people who are watching this just want to be able to get the kind of basic output without getting into the nitty-gritty details. So we're not going to spend too much time on actually going through the vignettes, and I'm going to show you essentially the easiest way to use these things in a usable manner. Specifically, I'm going to teach you DE-seq2. Again, there really isn't a wrong answer. I think DE-seq2 though is effective, consistent, and it starts right from your raw counts and goes from there. So you don't have to deal with any kind of normalization, and you don't have to deal with building any kind of models in which your process used, which is what lemma and edgeR both start out as. So we're going to focus on DE-seq2, which again, like I said, Michael Love, who was the author, spent a lot of time crafting out a very extensive vignette with a lot of Q&A and a lot of troubleshooting. So there's plenty of there to read. And it's a bioconductor package, so it's installed rather simply. Now, after you perform analysis, you're going to get something that looks like this. So I wanted to spend a little time talking about these results before we do the demo. So as you can see, the outputted table will have all of the features that you tested along the y-axis, and then a number of values per feature along the x-axis. The base mean is the average expression of that feature across all samples. This is an important metric because sometimes you can get features that look to be differentially expressed, but are so low expressing that actually the very slight alterations that occurred led to exaggerated results. In fact, a lot of these tools now have mechanisms built in that can compensate for these low expressing high variability genes that will ensure that they won't come out significant unless they truly are different. Log2 fold change is the effect size of your difference between your two groups. It is basically just the log2 of the average expression of a treatment over the average expression of your control group. Note that again, that there's an underlying model that is used for this analysis. So if you just do this calculation, it will not be the same as the one that comes out here, but it'll be similar and of course in the same direction. The LFCSE is just the standard error of your log2 fold change. The stat is the statistic that was generated to help generate the p-value. P-values, hopefully people are familiar with, is a metric of how often these things happen by random chance. There's a more technical definition, but I'm not going to get into that. And then there's the adjusted p-value, which is the p-value that has been corrected for multiple hypotheses. So I'm going to spend just a minute here talking about statistics and the importance of their proper use when looking at results. So a lot of analysis ends up with that where the experimenter or the investigator just wants a list of genes. They want to know what's different between A and B. Now, the way these are decided are oftentimes decided by the p-value and the log2 fold change. I should note here that there has been recently a movement against just blind reliance on p-values. And although a p-value is an important metric when you're picking out genes that are differentially expressed, it is not your only one, and you should justify the p-value that you are using. Second of all, the adjusted p-value is an incredibly important metric that people oftentimes overlook. There's a little comic here, which I think explains it beautifully. The basic idea is that when you do high throughput multiple hypothesis testing, such as differential expression, where you have 10,000 tests, there's going to be a certain number that are going to come up significant, regardless of what the underlying truth is. This is purely to random chance. Because of this, it is very, very important that you correct these p-values to try and reduce the false discovery rate of these features. Now, with that being said, there are certain scenarios where you only want to use the nominal p-value as opposed to the adjusted p-value. For example, if you have multiple analyses in which you are trying to overlap your comparisons, I would argue that using a nominal p-value can be a little more justified because you are essentially not blasting your entire results. You're actually looking at a subset from across multiple comparisons to then draw from. In general, though, when you are just doing an A versus B comparison, you want to stick with your adjusted p-value. I see we have some question. Base mean incorporates both the low expression count information and variation, so more explanation could be helpful. So the base mean, as mentioned before, is the average expression of the features across all of your samples. Inherent to this number itself does not actually include any information about the variation between samples. With that being said, what the tools themselves rely on a model and underlying algorithms to basically rule out those features that it determines are too low expressing to be considered significant, despite the changes you'll see. So there's an example actually in this table which illustrates this quite nicely. You have a number of features that you have 6 features here, and you have this feature here that had a 0.25 log2 fold change in the negative direction and has a very low p-value. So it's saying that with this change, we're quite confident that this is in reality, because look at the size of just the basal expression of this feature. So this change might not seem that large, but with that, considering numbers that size, they can still be considered significant. Where on the other hand, this feature has an average expression of 6 across all of your samples, but it actually has a larger difference between A versus B. But not only is the p-value not significant, it doesn't even calculate your adjusted p-value. And it does this because after assessing the overall distribution of feature counts in your population, the model will then essentially set a cutoff where it says, actually, these genes below this level aren't even worth looking at. And because there's so much variation, but as such a low expression, the results are considered unreliable and it will exclude those samples from analysis. So that's pretty much it as far as things that I wanted to go through for my slides. I think the most useful thing I can do at this time, though, is show a live demo of what this actually looks like in practice. So I'm going to close out of these slides, and you can follow along at home. So I'm going to take this link here, which is on the first 2 pages. I hopefully made this open to all, so it should be sharing for everyone. In here, you'll find the slides that we're using right now, but you will also find these 2 folders, code and data. I'm going to start actually with the code. And I'm going to download this file right here, which is the DG Analysis 1 HTML file. As you can see, I've already downloaded this before. So this is an R markdown file in which I'm going to walk us through and see what differential expression analysis looks like in real time. Using this workflow, I'm going to essentially just be copy and pasting these blocks into an R script here and running it live, so you can hopefully see that it's not too hard, and that way we can also troubleshoot anything that comes up together. So we'll be using a data set that's commonly used in the R world called the Facila data set. This is actually a separate package, but to make things easier, I'm not even gonna have you load that package, even though I am here. I already downloaded that data for you and put it here. So in the data folder, same thing. You can download both of these files. As you can see, I already did this before, but I'm just doing this again just so we're all on the same page. And after I have downloaded both these files, I'm going to read them in. So as it says in the first section here, we're going to load in these files. Now, as a general good practice in coding, I like to read in files like this, where basically I will set a variable that has the full path to where the file is. A little tip for those, I think on Mac, I'm not sure it works on PC, but if you want the full path for a file, all you have to do is copy a file, so Command C, and if you paste it, quote unquote, into a terminal, then it will give you the full path. And from here, you can copy and paste this into your R script here. Same thing that I'm going to do with the annotation file. I'm just going to copy and paste it just so I can grab it, and I'm going to put it in here. Now that I have my count file, my annotation file strings available, I'm now going to read them in as tables. You can see that this is what my count table looks like, and this is what my annotation table looks like. Now, as I mentioned before, the first step that we want to do with any of these experiments is to pre-process our data. So there's two things I want to do here. One, we are going to want to do some filtering of counts, as I mentioned before. But two, we want to actually make sure that our data and metadata are comparable. Specifically, I want you to look at the row names and the column names of our two tables here. You'll see that they're not exactly the same. First of all, they're out of order. Second of all, these row names, which are the sample names in our annotation table, have this FB attachment to all these. Now, it's really, really important that when you're doing this analysis, that your data and your metadata has the same sample IDs. Computers can only understand exactly what it is that you put in. And if there's any variation, it will confuse itself. And if it's out of order, it will not necessarily know they're out of order. So we're going to run a couple lines here to make these things the same, and then we're going to reorder them. The first line we're going to run is this. So we're going to reassign the row names of our annotation table by subbing out this FB section for a blank using the row names of our annotation table. So here are the row names of our annotation table as is. We're going to run this line, and then we'll see that the row names have changed. And then we are going to reorder the columns of our count table using these row names now. So we're going to grab our count table, and we're going to take all the rows, and we're going to index our columns using these row names. So just to emphasize, the current column names of our count table look like this. And you can see that they're the same, they're out of order. So just like in the same way, we can grab a specific column by name if we did this. We can also use a list of names to reorder them. So basically what this line does here is use the order of the row names as currently in the annotation table to reorder our count table. And now you can see that our count table is reordered. And as a check, we can run this line, which will see if these two things are identical. And yes, they are identical. So now that our data is properly formatted, we are going to filter our reads. Now, as I mentioned, I have a particular method that I think works quite well, which is applying a minimum number of reads to a minimum number of samples. So you can see here that I am setting these parameters outside of the call itself, as I want at least 2 reads in at least half of the samples. Here you see that I rounded the number of columns of the count table in half, and then I rounded that number up to be 4. So now what I can do with this one line is I can say, okay, return to me all the values that are greater than 2. I'll just head this, you can see what it's looking at. You can see how these are all false because they're all less than 2. These are all true because they're all greater than 2. This is true, false, false because this is 4, 0, 0. So this is greater than 2, these are not, so on and so forth. So I will now take the row sum of that, which will basically return to me how many trues there are in each of these rows. Oopsies. And then I can, then I want to ask and see how many of these rows have, sorry, how many samples have at least this value. So this whole line will end up being a one-liner, as we like to call it, to help filter out our reads. So let's run this. And you can see that it actually has a pretty big effect. So our original count table has 14,599 features. Our filtered count table has 8,000 features. So we actually excluded a lot of features in the filter. But again, this was a very lenient filter that I applied here. So these samples that we excluded, these features that we excluded probably don't need to be in there. And we want to get rid of them because 1, they can kind of just clog up the model. And 2, if the model does not automatically drop those, as I mentioned, some do, but some do not, then you will essentially be testing a lot more hypotheses than you need to. And as I mentioned before with the multiple hypothesis correction, it is a great benefit to you to not waste your hypotheses on things that are almost certainly just not going to be real, and because statistically you're essentially going to pull up garbage, and you want to make sure to avoid that at all costs. So by doing this, you're going to get rid of features that you know will most likely not be viable to begin with. So now we have a filtered count table that's properly formatted and a metadata ready to go. So the next part of this is probably the trickiest part. So I'm going to go pretty slow through it, which basically we have to tell our tool what comparison it is that we want to do. Now, the DE-seq literature will have a number of comments on how the proper way to do this. This is just the way that I do this. There are many other ways to do this. This is, I'm not saying this is the only way, but this is a little bit of a longer method, but it's a little more foolproof. And I think this is nice because this will enable you to essentially copy and paste this into your own work and just plug and play whatever data it is that you're currently using. So if we look at our annotation table again, we have several columns of metadata. The comparison though that we want to look at is this first one here, this condition column, where we have treated and untreated samples. So the first thing I'm going to do is I'm going to pull out and say, okay, I want all of my samples that I'm going to call treat as to be labeled treated, and all the ones I want to be controls to be untreated. Now I'm doing this because if, for example, in your data at home, you have an entirely different data set, but your treat cohort is red, and your control cohort is blue, then you can just change these strings here to red and blue. And you can essentially use the same code snippet to create the same thing. So using this annotation column, using this annotation table, I'm going to grab the condition column and assign this as this new variable called DE-seq anno table. So it just looks like this. And what I'm going to do is I'm going to go through and we're going to pull out all of the samples that are equal to our treat label and call them treat, and all the samples that are equal to our control label and call them control. And then I'm going to factor them, and I'm going to rename this column with DE-seq label. And that's what all this does. So you end up with something like this. Now to reiterate, when you have your own analysis at home, you will have your own cohorts and your own labels for your treatment group and your control group. But as long as you change the column you're grabbing, and then whatever labels you want to use as treat and control, you'll still end up with this same end result. And this end result needs to look exactly like this, because the way that you have to input this into DE-seq is you have to create an object that looks a little something like this. So we already went over our count table and our annotation annotation table, which, just to recall, our count table looks like this, and then we just created our annotation table. Now, in the design formula looks a little something like this. It's a little tilde, the squiggly sign, and then DE-seq label. You'll recall that I manually set the column name for this annotation table as DE-seq label. Now, if I didn't do this, whatever column it was before, let's say condition, we would have to do tilde condition. Now you can see that using this kind of hard coding like this will make your code not reusable time and time again. Now you have to remember exactly what it is that you need to use at what parts. So again, to reiterate, by using this little code snippet here, you can basically put in any annotation table you want, and as long as you label which samples you want as your treatment group and as your control group, it will do the rest of the work to create an annotation table that will play nicely with the DE-seq algorithm. So after we have created this, we will create what's called our DDS object, which takes in all of these things and creates a singular R object. And after that, the actual execution of DE-seq is as simple as this one line. Now, I will say that there's other things you can, of course, do with this execution. There's other parameters that you can do that I'm not going to get into. But as far as, again, as usability and to do the most basic thing possible, all you have to do is run this single line once you've created this object. When you do this, it's going to give you a couple outputs as it runs through the algorithm, and then you'll have the results. To actually get the results of it, you will want to use this line. The results function of DDS will give you something that looks like this. That will have a couple other things on here that are important to note, but you won't want later, which is why you can just mark it as a data frame. But just to go over them quickly, basically what this shows is this shows you the comparison that was actually done. So you can see that this did your treat over your control. I'm going to say it again, treat over control, treat versus control. Now, again, this is another reason that we took the time to make sure that our annotation table is correct, because it will know that treat will go over control when you go like this. It'll actually pick out the factors and the ordering of them and how it does a comparison alphabetically. But again, I'm trying to avoid too many specifics because it'll just get confusing. If you adhere to just these guidelines as I followed here, it will always create, again, an annotation table with treats and controls, and it will always run analysis with treat over control. So for all these features, this is the treatment group over the control group, which means if it's positive, the treatment group is larger. If it's negative, the control group is larger. And so again, to grab these results, just to have it just look like a normal data frame, you can just say as data frame. Oops, yeah, and then you'll just have your normal data frame. Now, as I mentioned before, this is what the output looks like with the base being multi-fold change, et cetera, et cetera. So this is basically your end result. The only other thing that I wanted to go over, which is something that's worth mentioning because it's actually pretty commonplace, is the idea of using covariates in your model. So when you're doing these differential expression analyses, as I said, the most important piece of metadata is your A group versus your B group. Oftentimes, though, there will be a number of other factors that can contribute to the effects that you see. So for example, a very common thing when working with patient cohorts is that you want to do some kind of controlling for age or sex. Another thing that can occur is you can have batches that you want to control for. You can also have paired analyses where you actually want each pair to be considered on its own. All this information is important to the model itself because if you don't include it as some parameter, it's going to ignore the information entirely and your results won't be quite as accurate. So the second section, all this first part is the same. So although I'm going to run it again real quick, just note that it's pretty much everything we've done already. So there's nothing new here. But where things get a little different is that we have our annotation table as before, but I want to add on a control column. I want to add on a column that I want to essentially control by, which means it's going to include this information as a covariate in the model. In the same way that we built this annotation table, that in a little way that was a little extra coding, but made sure it was pretty foolproof, We're going to do the same thing with the control column. So a lot of this code here is a little more complicated, and I'm actually not going to spend the time to go through the individual lines of this. I will say, though, that it all starts with just this section up here, where you're going to pull out whatever control columns you want. So as you recall, our annotation table looked like this. And in this example, I'm going to have us control by the type of sequencing that was done to generate this data. You can see we have a mix of singled end and paired end data. In general, that's not a good idea. Just as an aside, you don't want to do some run single end and some runs paired end. They generate quite different results. But again, if it's all you're left with, then it's what it is. So we're going to try and control by this in our design formula. So we have to include it somehow as a factor. So basically what this is going to do is by grabbing this control column, which just looks like this, we're going to run these lines here, which are going to turn this control column into a separate table that we're going to attach onto our annotation table, and we're going to label it control variable 1 or whatever number it was. So you end up something like this. Now, again, these lines are a little complicated, but as is written, basically what they're going to do is they're going to take this new control column, they're going to match it up to make sure it's in the same order as your original annotation column. It's going to merge them all together, and it's going to output a table like this. Now, in the same way that this previous code snippet made it so that our main variable is always called DESeq label, this is going to call each of the control columns that you have control var 1, 2, 3, ... And this is useful because as doing this, we will then be able to have these category names to be able to plug into our new design formula. So this time, when you create a design string to create our DDS objects, we can just run this code here, and you'll see that basically it took whatever control variables we had, and again, if it was 1, 2, 3, ... n, it would have these 1, 2, 3, ... n, and then plus DESeq label. Now, the construction of this string is highly specific because basically what this string does is it will take the last variable as your condition that will be your A versus B, and everything else beforehand will be the covariates that it'll include in the modeling to generate your differential expression analysis. So the order of these things do matter a lot, but the specific order of having this one be at the end is crucial, because if you swamp them, basically what you're going to do is you will control for your treat versus control column, and you'll actually be testing for the difference between single versus paired end, which is not what we are trying to do right now. So now with our new design string here, we are basically going to create a new DDS object using this alternative design string, and with this, we will be able to then run our analysis. Note, this text that come here might look scary, but all it's saying is that it doesn't like these dashes in here. It wants them to be underscores instead. Not a big deal. So you have a question, should the covariates be only binary? Could DESeq2 deal with categorical levels greater than 3 covariates? Yes, the answer is yes, yes, yes. You can have as many levels as you want with your covariates, but a word of caution. The author and everyone else who uses this recommends that if you use something that is truly continuous, for example, like age, then you bin it first. So you don't want to have ages 20 through 80 in there. You want to bin it, 20 to 40, 40 to 60, 68, or something like that. Because within the model, if you have one factor that is red, blue, green, it's going to recode that as 1, 2, 3. And then if you have your age as 40 through 80, the exaggerated effect of the difference in ages will skew your model. So you can have as many levels as you want, but if you have continuous data, I'd probably bin it to keep around, I don't know, 5. And that's kind of hand wavy. It's kind of a ballpark number, but I think that's in general what I do, and it tends to work pretty well. So after we have our new DDS object, running DESeq is again as simple as it was before. It's a single line. Note here that I wrapped the DESeq call in this with a suppress messages function. All this does is clean up the output so it's not as noisy. So now when I run this, it's going to run through the algorithm. It's going to generate the results, and then to pull out the table, I am going to do results and then as a data frame, and we'll have it there. So that was pretty much everything that I wanted to cover for this. As far as writing this information out in the same way that you read in this table, I would probably, in a similar way, write it out as a CSV file. So you'll have an out, let's say like an out DE-seq file. I'm just going to write it out to wherever I got this data. I'm going to call it DE-seq out.csv. And then I'm just going to write my table out. Oops, I had to put the file in there. And you'll see in this folder, we now have our output, and it looks like this. So that was pretty much everything that we wanted to cover today. There are several other tools you can use, like Limma and edgeR, that work in similar ways. I'm going to say again that DE-seq2 is probably the easiest because Limma and edgeR require you to build the linearized model that you then have to run your analysis on. In the end, it's not that much more coding, but it is a little more complicated. Hopefully this vignette that I created will allow you to plug and play any of your own analyses in there to run. If you follow the sections that I had here about the design strings for your DDS object, it should rule out most of the issues that you'll run into. And I think that's pretty much it. Next time, we are going to talk about DE-seq visualization. So what you can do with your results once they're done. We're going to cover things like volcano plots and heat maps and PCA plots. And we may talk a little bit about gene set enrichment analysis as well. If anyone has any questions, I will stick around for a little bit. Otherwise, thank you very much. And I hope to see you guys on Thursday.